Okay, today we will talk about memory, particularly DRAM. So we talk about a lot SRAM, static RAM. So as long as you power up the SRAM, the data can be stored in the SRAM. But when you cut off the electricity, and of course the data will be gone. Today we will study another type of memory, which is a so-called dynamic RAM. Even you do not do anything, the data will spontaneously leaking away from the cell, from the memory cell. This is because of the nature of DRAM. So, well, we have a very leaky cell in the DRAM. Why do we need a DRAM? After all, the answer is simple: higher density. Nowadays, even you open your web browser, Chrome or Firefox, the memory consumption will be even more than 4 GB. This is not a trivial memory capacity. Even you just use your laptop to watch some YouTube videos. So we need a lot of memory space. This is even your daily use, not for high performance computing, for scientific applications. For those big data, high performance computing application, we need more memory space. Then we need a DRAM. So DRAM only use one transistor to record one cell. But the SRAM, recall the SRAM structure. We have two inverters in the cell to serve as a cell in a SRAM array. So two inverters cost your 4 transistors, and you also need 2 access transistors. So totally there are 6 transistors to record 1 bit. But for DRAM cell, you just need 1 transistor plus a capacitor to record the data. So even the DRAM is not perfect. It's very leaky. You will lose your data spontaneously. We need that type of memory because of the high density, because of the small hardware overhead. So this is the SRAM cell. 2 inverters, 2 access transistors. This is the DRAM cell. We only have 1 access transistor here and a capacitor here. So this capacitor is a so-called trench capacitor. How to make a transistor in your chip on the die? The fabrication company just dig a very deep hole here to serve as a capacitor. So you can consider that, making one of this hole is very easy, but make billions of holes on the same die, and they should have similar depths. More perfectly, they should have the same depths. They should have the same dimension. That's very difficult, particularly now everything is in nanometer scale. So it's really difficult to fabricate the DRAM. That's the reason why nowadays you only can buy DRAM from Micron, American company, Samsung, South Korean company. Just few company in this market. Smaller company cannot have so perfect fabrication technique. Even you can make a chip, but at a very high cost. The yield will be very low. Only these company can, make the DRAM in a scalable way, so that they can sell you the chips in a very reasonable price. So this is the organization of the DRAM memory. It's similar to the SRAM. You just need to replace the SRAM cell with the DRAM cell. You also need a decoder, row decoder, and a column max. But the DRAM is much denser than the SRAM because the cell area is smaller. So DRAM cell is a single-ended. Each read is destructive, which means that each read operation will destroy the content in the cell. I will talk about more on this. And we also need a row buffer to hold the read data because first, the read operation is destructive. You need to keep a correct version of your data in somewhere. So the row buffer is a good place to do that. Second, the read operation from the DRAM cell is very slow. You need some buffer so that you can read the buffer in a very fast speed. I will talk, of course, I will talk more on the row buffer in the following slides. So here is the destructive read. We use a capacitor to store some charges to represent the data. If you have some charges, then it represents 1. If you do not have charges, then it represents 0. And this is the access transistor. Assume that, let's start from the one case, which means that you have some charges. Then the cell has the VDD voltage because it's full of charges. The voltage of the cell is a VDD. And we need to do an operation on the bit line, which is the bit line. This is the bit line. We need to do one operation on this bit line. We need to pre-charge the bit line voltage to 0.5 VDD to initialize the read operation. Then here is the 0.5 VDD. This is a bit line voltage. So let's review the read operation. At the beginning, we needed to charge this bit line to 0.5 VDD. And then we needed to select one row. Assume that we are selecting this row. What do you mean by select? Select means that I send a 1 here, but all zeros to other rows. Because here is a 1, then the transistor is closed, which means that the cell is actually connected to this pre-charged bit line. So here is where the connection happened. So at this period, the cell is actually connected to the bit line. The bit line voltage is a 0.5 VDD. The cell voltage is a VDD itself. Then apparently the charge will flow from the cell to the bit line. Why? Because the bit line has a low voltage and the cell has high voltage. You can see that when the charge is reducing in the cell, the voltage is reducing too. And when the cell flew from the cell, when the charge flew from the cell to the bit line has more charges, then the voltage of bit line increases. Then the sense amplifier, here is the sense amplifier, can actually sense this voltage difference on the bit line. So this is how we read the content of the cell. But the content in the cell has been destroyed. Why? Because now your cell has a maybe 0.6 VDD, maybe 0.3 VDD, maybe 0.5 VDD. The voltage in the cell is not a VDD anymore. The cell cannot represent a good one. So the same case will happen when you have a 0 here. If the cell has no charges, the cell voltage is VDD, and the bit line voltage is pre-charged to 0.5 VDD. Now, because the cell voltage is low and the bit line voltage is high, then the charge will flow from bit line to the cell. Then the cell voltage increases, but the bit line voltage will be dragged down. By the cell. It will go to maybe 0.1, maybe 0 VDD. And the sense amplifier can also sense this difference. Now, in your cell, you have a 0.1, 0.2, 0.3, 0.5 VDD. But anyway, it's not a 0. It's not a no charge. It's always it's not fully charged either. So we call this the content in the cell has been destroyed by the read operation. So this is why we call the read operation in the DRAM has been destroyed. So now the content in the cell has been destroyed. Where is your correct data? The simple answer is your correct data is actually in the sense amplifier, because now the sense amplifier know whether you have 1 or 0. Then the sense amplifier can write these data into the row buffer here. These are the cells. Blue color indicate 1, red color indicate 0. This content will be read, will be sensed by your sense amplifier here. And then the content in the cell will be destroyed. And then the content will be written in the row buffer. So the row buffer now have the correct data of that row, entire row. And then the row buffer can write these data back to the DRAM cell, back to that particular row. When you read your data to the sense amplifier, to the row buffer, this operation called open one row. When you try to restore your data to that row, this operation is a so-called close a row. Because after you close this row, you can use the bit line, you can use the sense amplifier and the row buffer to read another row. Open a row means you starting to read that row. So if at this, after you open a row, your data has been stored in the row buffer. Now, if some request ask for the data in this row, you don't need to read the cell anymore. You can directly send out the data through the row buffer, because the correct data has been stored in the row buffer. And the reading from a row buffer is faster than reading from the DRAM cell. Why? You can see that there is some charge sharing operation when you read the DRAM cell, and the charge sharing is very slow. particularly with the tiny, capacitor of the DRAM. So even you do not touch the cell, even you do not read the cell, because the cell uses some capacitor to store the charges, and the charge will leak away spontaneously away from the cell, like this. So your cell's voltage will gradually and spontaneously will reduce. Eventually, it will reach some threshold. When you reach that threshold, your sense amplifier cannot recognize whether it's a 0 or 1 anymore. Then what can you do? You can, periodically read the content out and store the content back. This is a so-called refresh operation. So now this operation happens in your cell phone now. Nowadays, even your cell phone has a 4 GB memory or 8 GB memory. And your cell phone is doing this refresh currently. That's the reason why even you do not use your cell phone still, the battery of your cell phone will still die. So there are, different refreshing policy. The first one is burst refresh. You stop everything. You stop the CPU, stop your operating system, and refresh all the memory. And this is not good because during the refresh, you cannot use your CPU, your mobile phone anymore. And this will result in a very bad user experience. All you can do so-called distributed refresh. Means that you do the rotate, you refresh one portion, CPU can use another portion, and then you move to the other portion, and the CPU can use the DRAM you just refreshed. So this way is better, but eventually you need to do the refresh. The third one is a self-refresh. The refresh operation actually is manipulated or managed by the CPU. If your mobile phone is in idle case, you would like to shut down your CPU or put your CPU in a low power mode, which means that CPU cannot manage the DRAM anymore in that state, in the low power state. How can you handle the refresh? If you do not handle the refresh, the data in the DRAM will be gone. Then you can ask a DRAM to manage it itself. The DRAM is really stupid. It cannot, actively do some commands. It can just listen to your CPU. But in order to support this low power feature, DRAM company just add a self-refresh mode for the DRAM. Then at least your DRAM can refresh itself periodically. So here is a typical memory access, DRAM access sequence. First, your CPU will run some applications, and the application will issue a DRAM command, DRAM request. The DRAM request will go to the memory controller. Nowadays, the memory controller is a part of your CPU. So these are your CPU chip. The memory controller can do some scheduling, can temporarily store this request in some buffer. Eventually, it will issue this request to the DRAM. Like I said, the DRAM is really stupid. So your memory controller need to translate this high-level request to some commands the DRAM can understand. Stupid means it's cheaper. You don't need to add fancy control on the DRAM. Even it's cheaper nowadays. I believe if you buy 32 gigabyte memory, it's equivalent to your CPU. The price, I mean. So the memory controller need to translate the high level request to some low level comments. The first comment is activation. Activation means you enable one word line. After you enable the word line, touch sharing happens. The data will be sensed into the sense amplifier. And the sense amplifier will write the data in the row buffer for the entire row. And then your controller can inject some column address. What does that mean? It means that I only need this portion of data. I don't need your whole row. The whole row, I don't need the whole row. I just need the first half, maybe the first quarter of the data. And then the DRAM chip will send the data the memory controller asks for to the memory controller. This is so-called transfer. And eventually the memory controller will send the data back to the CPU. Even for one read operation, you can see we have multiple steps. We have a lot of queues to buffer the comments, to buffer the requests. First, the CPU generated request. Second, the request will be sent to the memory controller. The memory controller can do some scheduling, can translate the high-level request to low-level comments the DRAM can understand. And then the memory controller can active one row of the DRAM. Second, the memory controller can send the column, sense column address to the DRAM so that the DRAM eventually will send a part of the row back to the memory controller. And then the memory controller will send the final data to the CPU. So you can see that latency should be calculated by all the sum of all the latency of all the steps here. And then the comments, the data, everything will be represented by the binary waveform. You can send the request like this. The row activation address, the column address. Of course, this is address bus and this is data bus. After you have these two address, I can give you some data. I can give you some data now. Row address, column address, and then the data. So if you only read one row, read the data on the same row, you don't need to repeatedly to send the row address. You can just give me the column address, and then column address, and then the data will be pumped out from that particular row. So this is so-called fast page mode. One page will be stored in one row. So this is how we manage the virtual address to the physical address. The virtual address concept page will be translated to one physical row in the DRAM. Now the DRAM company even create a more advanced, faster read mode, which is a burst mode. You just send one column address, and then I'll give you 8, 4, 16 bursts of the data. Of course, this is a consecutive data in the row. So in this way, the DRAM can serve the sequential access better. So that's the reason why, no matter from a cache perspective, no matter from DRAM perspective, no matter from a disk perspective, sequential access is always preferred. If you are the programmer, you need to developer, you need to have more sequential access. And now the data transfer can happen not only on the rising edge, but also the falling edge. So in one cycle, 2 data package can be sent. This is so-called double data rate, DDR. Now we have a DDR5, DDR4. So they have a more advanced feature, but eventually the DDR means in one cycle you can send 2 package, one on the rising edge of the clock. The second one is on the falling edge of the clock. And again, DRAM use binary to represent the data. High voltage means 1, low voltage means 0. And the transition from 1 to 0 or the transition from 0 to 1 is a so-called setup latency. And of course, you hope the setup latency is shorter. Means you have a very steep curve here. You don't want to have a curve like this. Slowly increases because the setup will cost a super long latency. You hope you can have something like this, very steep signal. Then the setup can be finished maybe in 0.01 nanosecond. You hope you can have a this type of latency. Considering the setup latency, considering the data transmission latency, you hope that some signal can arrive simultaneously. While other signal, you hope other signal will arrive sequentially, and some signal will arrive simultaneously. That's the reason why they have this, bizarre curve on the motherboard. So by adding some distance or reducing some distance, they can maintain the timing of the signal. Because now we have the page. Now we have the row buffer. These are expensive resources, faster resources, which need to be shared by the entire DRAM chip. The chip can have the same concept as and DRAM chip can have the same concept as SRAM. You can have multiple banks. The bank is the minimum unit, which can be independently read and write. With the row buffer, you can have a different policy to manipulate the row buffer. And the bank. Assume that you have n banks here. You can put your data like this. This is your first word, second word, third word, and then n minus word. And then you can put n word here in the bank 0. So you can manipulate the layout like this. In this way, you expect that, for example, you declare a long variable. This long variable will occupy, of course, multiple words, sequential words. So this long variable let's call it A. This A will be stored in multiple banks. Assume 4 banks. When you read this A, you can issue the request to all these 4 banks. In this way, you can take advantage of the so-called bank level parallelism. This is good. Otherwise, if you put all the data in one bank, for example, bank 0, you have to read this bank 4 times to have this variable A. So this is the organization of your DRAM. So this is DRAM. This is not a chip, but this is so-called DIMM. D-I-M-M. I cannot remember the full name, but this is some kind of a module, DRAM module. This is so-called DIMM. On one DIMM, you have a lot of chips. Each small square here indicate a chip. And inside each chip, you have a different arrays, and you have different banks. So all the banks share the same address and control pins, means they share the same address bus and control bus. But all the banks are independent. You can talk to one bank at one time. Multiply A times A means each DRAM output 8 bits. So it needs 8 chips for DDR-X, and each burst of the DDR is a 64-bit. So that's the reason why you need 8 chips, and each chip has 8 bits. But typically you have more than 8 chips on the DIMM. Why? Because you also need a ECC. We talk about the ECC and parity, how they can prevent the errors, how they can detect the errors and correct the errors. The easiest way is that you have one memory controller on your CPU, and then it can talk to your DIMM. If you now, even your mobile phone has multiple DIMM. So you can have 2 DIMMs here. Each DIMM can have a DRAM memory component. They share the same command bus. This is the shared command bus, but they have a separate data bus. All you have a 2 memory controller, and each memory controller can be in charge of managing one DIMM, which means that each DIMM has its independent command bus and data bus. And of course, the last case is the best, has the best performance. Why? Because every resource is an independent resource. You don't have any sharing. You don't have any conflict. Any sharing can potentially result in conflicts. And inside one bank, you hope that you can map consecutive address to improve the performance. Multiple independent channels can help you maximize your parallelism. Because if you map consecutive lines to the same channel, then you have to read everything sequentially. If you map them into different channels, you can read them parallel. And then you need to consider how to map the channel, how to map the rank, how to map the bank, so that you can maximize your parallelism. The rank means the memory chips controlled by one command bus. And we will talk about these different policy in the following slide. So this is the address mapping scheme, different address mapping scheme. Either you can map your data in this way. This is the first byte, second, third. And then you go to another bank. And then you go to another bank. And then you go to another bank. Or you can map your data like this. These are consecutive array, and this is another consecutive. These are another consecutive. These are another consecutive. Assume that each address here is one element in your array. And this is your second element, third, fourth element. First, I'm sorry, this is the first element, this second element, third and fourth element. And then you have a different, when you try to read this element, you will have different cases when you adopt a different mapping. For the first mapping, you need to read everything from the same bank. Because maybe all your array is in the bank 0. Even other banks are idle. You have to use only this bank. But remember, we have the row buffer, which means that when you select one row, everything will be in the row buffer. You can read the data from your row buffer in this bank 0. When you adopt the second mapping, you can simultaneously read all the banks. But potentially, the row buffer hit rate will be very low because you only fetch one element in that row. And the second element you want to read from that bank may not be in that the same row buffer. So which means that you have to activate the row, another row, and read everything again. So different policy have a different benefit. Which policy is which scheme is better? You need to test for your own application. The benefit is heavily depend on the read access pattern, element size. Different, of course, different application may prefer different policy. So these are some policy for different mappings. And I think I will talk more in the next lecture. Any question? If no question, here are our syllabus. So we have done the presentation 2. So if you have any question, please email me on the presentation 2. I know some of you didn't attend the first 2 presentations. So please do a better job in the final presentation. And this is a graduate course. We don't have examination. So the third presentation will be our final presentation. Before that, we will talk about the DRAM, non-volatile memory, some assembly language, and one example of all the applications, which is how to design a hardware accelerator for genome sequencing application. And then we will have a final presentation on your project. I don't want to occupy your busy time in the final week because we don't have examinations. So I would like to finish everything before the final week. And in the final week, if you have any question on your credit of this class, please schedule some individual meeting with me, or we can use the class time to talk about your credit of this course. And then you can do some makeup presentation or deliver some makeup results to improve your final results. Any question? If no question, we can stop. Thank you very much.